First stage, main engine ignition. Lift.
Hi, this is a lecture on atmospheric absorption, and it forms part of the undergraduate honours option in remote sensing of global change. Now this is a graph showing the energy lost as it's passing through the atmosphere. It's just a rough diagram. I haven't put any numbers on here. I want you to just get a sense of the general trend of this graph. And we looked a little bit at it in the lectures. You notice the axis at the bottom here is the wavelength going one direction, or increasing energy from left to right. And just for reference, I've put in the visible part of the spectrum there so you can see the little rainbow colours. So off the end of that to the very far right of the diagram, we're going into the ultraviolet, which is no longer, our eyes are no longer sensitive to that part of the electromagnetic spectrum. And then below that, into increasing wavelength, we go off the red end of the visible part of the spectrum into the near infrared, NIR, then into thermal infrared, which is primarily originating from objects of temperatures of a few degrees C. And as we get to longer and longer wavelengths, we get into the microwave region, and then radio waves right off the end of that. So microwaves are up to a few centimeters in wavelength. Now what this graph is showing is how much energy is lost in passing through the atmosphere. What we can also show in this diagram, the sort of typical language used in climate change, looking at the greenhouse effect, as we think about shortwave, which is really into sort of the visible, a little bit into the near infrared. So it's shorter wavelengths, high energy radiation coming in from the sun. And we talk about the long wave part of the electromagnetic spectrum, which is really talking about the thermal infrared. It's not really referring to the microwaves much, because in the context of climate change we're really interested in that shortwave, long wave distinction. And you'll notice that this diagram effectively encapsulates the greenhouse effect, is that shortwave radiation gets through the atmosphere. So this curve is very low down, lots of energy gets through. But at the long wave part of the spectrum, there's lots of loss of the energy passing through that. The energy in that electromagnetic radiation is actually being absorbed by the atmosphere. So shortwave radiation comes in from the sun, warms up the Earth's surface, but that emitted radiation in the long waves doesn't get through the atmosphere. Now just to give you a visual interpretation of what this diagram means, here's the Earth completely cloud free, and what I've just done is turned that diagram very roughly into sort of opacity. So the opaque bits on this overlay here is where you can't see through the atmosphere, so there's all the energy is being lost. But there are gaps here where the opacity is quite low, the atmosphere is quite transparent, and you can now see through down to the surface. You can see in the visible part of the spectrum it's very clear. We're assuming there's no clouds here, of course. And right down into the microwave part of the spectrum it's also very clear. So these are the two main parts of the electromagnetic spectrum where we would consider using satellites making measurements at these wavelengths to look at the Earth's surface. And that's why we refer to these areas as atmospheric windows. The atmospheric walls are where the atmosphere is blocking all that energy, it's absorbing it all. So that lots of the energy is being lost when it's being passed, when it's passing through the atmosphere. And this diagram is just trying to represent that. So the atmospheric walls you can't see through, the atmospheric windows you can. In the near infrared, this is going to be a challenging place when we try to look at thermal measurements of the Earth's surface to say look at sea surface temperature, because we want to try to look through some of these narrow windows and see through down to the Earth's surface. If you want to measure properties of the atmosphere, of course, is that you might look at these areas which are kind of moving between atmospheric windows and atmospheric walls, because they are giving you a variety of different depths into the atmosphere. If you look just make measurements just in the atmospheric walls, you're actually seeing just the top of the atmosphere, because the atmosphere then becomes so thick that any radiation from deep into the atmosphere doesn't reach the top of the atmosphere. So you're only really seeing the top of the atmosphere. So let's try and in this little video lecture I want to look at a bit more detail about where the shape of this curve comes from. If it helps you, you can turn this diagram and flip it on its head, and then we're actually looking at this is the energy that passes through the atmosphere. So in the thermal infrared here in the atmospheric wall, no energy is passing through, whereas the atmospheric windows, lots of energy is passing through. You'll see different versions of this diagram drawn in different directions, either increasing wavelength or increasing frequency. Sometimes it's the amount of loss through the atmosphere, sometimes it's how much energy gets through. So the opacity versus the transparency. So always be careful to look at the axes of any diagrams you see in any of the textbooks, because they may well be drawn in a very different way. Let's think of electromagnetic radiation for a minute. Electromagnetic radiation is conceptually something that's very difficult to imagine. Sometimes it's possible to model it as a wave. Okay, so we just think of some kind of wave field. Sometimes it's easier to consider them as particles, which we call photons. So the energy is moving through space in little particles. In actual fact, for many applications, especially when looking at atmospheric absorption, we have to try to think of it as a combination of the two. So in some sense you can think of little packets of waves. Another very simplistic way, and I'm just going to use this as one little tool to try to explain atmospheric absorption, is to think of or to visualize these little wave packets as being little blobs of energy that are vibrating at different frequencies. So I've colored them differently to sort of emphasize that they're different wavelengths, and they're also oscillating here at slightly different frequencies. So the red one's going slowest and the blue one's going fastest. So the blue one has got a bit more energy than the red one, and the orange one is sort of somewhere in between. And to conceptualize these as electromagnetic radiation, you have to think of them as flying through the air, or flying through space. Then you can conceptually think of, say, a molecule or an atom that has a preferential frequency. So much like the making the glass sing in the lecture, that this particular object, this molecule or atom, has a particular frequency that it likes to oscillate at. So if these little packets of electromagnetic radiation are passing by, if that frequency is too, if the energy is too high, or the energy is too low, so the frequency is too low, it doesn't do anything. It doesn't interact with this molecule or atom at all. And it will only be when an electromagnetic photon comes along that's of just the right frequency that it will start to oscillate in its natural energy state. We can expand that to think of molecules, so or collections of molecules, and you can imagine that if we combine this orange one and the blue one, then the longer wavelength, the red oscillations don't interact at all, but it will still interact with the orange ones here and absorb that energy. Different frequencies, if it doesn't match either of those energy states, it won't interact with it. So it requires just the right frequency in order to interact in such a way that the energy is absorbed by the molecule. And in this case there's two different energy states that this molecule will absorb. The other thing to realize, of course, is that when this molecule actually contains this energy, if it releases the energy as a photon, it goes back to its original state, and the photon that releases is of the corresponding frequency or energy. So in this case it emits two different frequencies. Here's an actual molecule. Now this is carbon dioxide. So one carbon atom in the middle, two oxygen atoms bound to it on either side. And just to illustrate kind of what we mean here in terms of the energy states in a more physical sense, is that here we have the carbon dioxide molecule oscillating in a symmetric way. It can also oscillate in an asymmetric way. And these two energy states are slightly different. So these would correspond to absorption or emission of particular frequency photons. And in fact, this molecule can also vibrate in a third way. So in terms of vibrational states, there's 3 different vibrational states that this molecule can be in, and that corresponds to 3 different frequencies. And we'll see in a later slide that vibrational energy states are not the only energy states that a molecule or an atom can be in. We can also look at electrons. It can also be rotational energy states. At the very high energy end of the electromagnetic spectrum, we're actually looking at energy states of the nucleus of the individual atoms. So here we are back at this diagram. And again, just to check that what we're actually plotting here, this is how much energy is lost. So that's the attenuation or the absorption through the atmosphere. And we're just using carbon dioxide here that doesn't correspond necessarily to a real line, but we're just using it as illustration. So what we have with this carbon dioxide molecule is that we have, at a particular frequency, the carbon dioxide molecules want to absorb the electromagnetic radiation. So at that one frequency, this line that's drawn here, the absorption is very high. And this is what we refer to as a spectral line. And in this case, it's a spectral absorption line. Now, in fact, it's not an infinitely thin line. There are a number of reasons that I'll leave you to find out in the lectures or by broader reading to realize that the line itself actually has a bit of a thickness to it, has a dimension that crosses a range of frequencies. But it's very close to being just a particular frequency. Now in this case the absorption is very high, so we can imagine in this particular lump of gas that we're passing electromagnetic radiation through, with lots of carbon dioxide at this particular frequency, lots of energy is going to be absorbed. If you don't have quite so much carbon dioxide, there's less absorption. There's less density of molecules to actually absorb the electromagnetic radiation. So if we were to plot the absorption line for a lower concentration of carbon dioxide, we'd see that the line had dropped. And hopefully you can see that this is our first stage here to looking at how you might measure some of the chemistry of the atmosphere. Because if you look at the absorption through the atmosphere, if there's a great deal of absorption at that particular frequency, you know there must be lots of carbon dioxide. If there's not so much absorption, then there can't be quite so much carbon dioxide. So in some sense we're starting to get a measure of the concentration of the gases in the atmosphere. And of course the actual atmosphere has a number of different chemicals in it. It's primarily nitrogen, but there's lots of water vapor. There's also molecular oxygen. We have ozone. There's also a number of gases, carbon dioxide, methane, which we refer to as greenhouse gases, of course. So a number of these lines, this looks like a very complicated diagram, but of course it's actually just the overlapping lines of lots of different chemicals in the atmosphere. So there's some carbon dioxide lines, there's lots of water vapor lines, and in fact this large atmospheric wall in the middle here in the thermal infrared actually corresponds to a vast number of water vapor lines that overlap so much that it almost becomes a continuous block of absorption. There's also another couple of a handful of lines from oxygen, both as molecular oxygen O2, but also ozone, which is three oxygen molecules. And in amongst there's also a number of different lines corresponding to different chemistry of the atmosphere. So what we're seeing in this diagram is actually the chemistry of the atmosphere. The absorption lines of each of the chemicals in the atmosphere absorbing at particular frequencies, and when you all overlap them all together, you get what looks like a rather more complicated diagram. It's this reason, of course, that we get the greenhouse effect, because it's the water vapor that's the major greenhouse gas, but also things like carbon dioxide, which if you increase the carbon dioxide, you're increasing the amount of absorption through the atmosphere at those particular frequencies, and many of the carbon dioxide absorption lines are in the thermal infrared or into the near infrared. Now I mentioned that it wasn't just vibrational states, it's also electrical states of electrons in orbits. The rotational states tend to be more into the microwave part of the spectrum. Once you're in the visible and the near infrared, we're looking more at electron orbits and the thermal infrared. So here we have our rotating electron. The yellow circle is our electron in this second highest orbit here. An electromagnetic photon comes in, it imparts the energy to the electron, and the electron jumps to a higher orbit. Now, in this particular mock-up atom that I've drawn, the red circle in the middle here is the nucleus of this atom. The electrons in these different orbits, there's 4 different electron orbits. There's 3 different jumps that this electron can do, going from one orbit to the next highest orbit. And because these orbits are actually fixed, and that the energy jump from one orbit to the next is a very discrete quantity, each of these jumps corresponds to a particular frequency. It's a particular energy, so it must be a particular frequency. But it can also jump up 2 orbits at one time, or even from the lowest orbit to the highest orbit in a single jump. So altogether there are actually 6 different energy jumps here, and therefore there are 6 different absorption lines. So any of these energy jumps can be induced by an electromagnetic wave if it has the right frequency that corresponds to each of these energy jumps. The same is also true of the emission. So this electron orbiting here in the highest orbital shell, if it drops down to the second highest, it emits an electromagnetic wave. So it emits a photon of the particular frequency that corresponds to the energy of that jump. So in terms of the emission lines, in terms of going from a high energy state to a lower energy state, there's also 6 different ways it can jump. And the highest energy jump here is from the outermost orbit to the innermost orbit. Now if we consider the spectral emission line, and we're just happy to be taking carbon dioxide as an example. It's not a particular line at a particular frequency, it's just for illustrative purposes. You'll notice again that we've now changed the axis here, so this is the energy emitted by the atmosphere, not absorbed. This is how much is emitted. So if you use a passive sensor to measure how much electromagnetic radiation is coming from the atmosphere, this is what we're going to plot here. Again, it's not an infinitely thin line. It's got some width to it. And again, as you might imagine, if you increase the concentration of carbon dioxide, if you have a high concentration of the gas that you're looking at, you will get lots of emission. There's far more molecules there to actually emit electromagnetic radiation. And if you don't have quite so much carbon dioxide, you don't have quite as much emission. The problem we have, and not one that I'm going to solve in this video, is that these 2 extremes also correspond to hotter or colder carbon dioxide. So if the gas is very hot, it will also emit more electromagnetic radiation at that particular frequency, because the molecules, the carbon dioxide molecules, if they're in a gas that is hotter, are moving about faster, they have higher kinetic energy, and as they do that, they knock into each other and actually knock the electrons into higher energy states, or they knock the whole molecule into a higher vibrational or rotational energy state. And so it emits more photons as the electrons drop down to lower energy levels. So these are the 2 problems that I'm going to leave you with. One is to think about what are the physical properties of the atmosphere that influences the breadth or the thickness of the line, both emission lines and absorption lines. And also, if you're measuring atmospheric emission, how do you differentiate between increased concentration of a specific gas and an increased temperature? Because in both cases, either increasing the concentration or increasing the temperature will increase the total amount of electromagnetic radiation that's emitted at that particular frequency. Okay, and that ends that brief introduction to atmospheric absorption. But there's some key ideas and concepts that you really need to understand in this lecture that help to explain how it is we're actually going to measure the concentration and or the temperature of the atmosphere.